Here is a phone call worth $200 million. It happens at 2 in the morning Taiwan time. The engineer making it has nothing to sell. No silicon, no software, no specification document. They have a relationship with one specific person inside the foundry. And 48 hours to convince that person that the design is safe to manufacture, even though it breaks one rule in the rulebook. A modern AI accelerator program books its wafer slots 3 years in advance. Mass costs at 3 nanometer are $30 million per set. Non-recurring engineering charges from the foundry are $50 to $100 million per chip program. Miss the qualification window because of one unresolved design rule, and the program slips an entire quarter waiting for the next available foundry slot. $200 million of cost, 6 months of lost market window. The phone call is what closes the gap, and the person making it is the Foundry Interface Engineer, the role nobody outside the chip industry has named that decides whether the architect's design can actually be built. 4 walls define the Foundry Interface Engineer's job. Every one of them is about translating between two organizations that speak different languages. Wall 1 is PDK Conformance. The process design kit is the foundry's contract with the design team. Every transistor, every metal layer, every via has a rule, and the design must use only what the foundry guarantees. A new version comes out every quarter. The engineer reads the release notes line by line and decides whether the design needs to update or whether to lock the current version. Wall 2 is DRC Waivers. Design rule checks flag every place the layout violates a foundry rule. Some are real, some are tool artifacts, some are real but safe in this specific context. The engineer triages thousands of violations and decides which go back to the design team and which go to the foundry for sign-off. Wall 3 is Allocation. Wafer capacity at 3 nanometer is a finite global resource. The engineer fights other customers for slots and negotiates with the foundry on schedule. Wall 4 is Process Change. The foundry tunes the process throughout its life. A small tweak can shift transistor characteristics by 2%. The engineer reads the change notices and decides whether to requalify. 4 walls, 1 person on each phone call. Wall 1, PDK Conformance. The PDK is a 40 gigabyte database that defines everything the design team is allowed to use. SPICE models for every device, design rule files for every layer, extraction views, parasitic models, layer maps, pin definitions. It is the foundry's promise that if you use only what is in this database, the silicon will behave the way the models say. Every quarter, the foundry ships a new PDK version. Sometimes it is a minor patch. Sometimes a single line in a SPICE model changes by 2%. That 2% will not show up in any simulation the design team runs. It will show up 6 months later when the silicon comes back with a critical path that misses timing by 50 picoseconds. The Foundry Interface Engineer reads every release note, cross-references every line against the design's exposure to that device, decides whether to update, decides whether to freeze, negotiates with the design team if a freeze means losing access to a needed feature, negotiates with the foundry if a freeze means losing manufacturability guarantees. There is no tool that does this. The release notes are written in the foundry's internal language. The implications require knowing which device family in this specific design is sensitive to which parameter. 6 months of context per program. No model can compress it. Wall 2, DRC Waivers. A complete tape-out database runs design rule check against 10,000 individual rules. The output is a violation count. On a typical AI accelerator at 3 nanometer, the first clean run produces 80,000 violations. Most are false positives. The DRC tool is conservative. A pattern that looks like a violation in 2 dimensions is fine in 3. A spacing rule that fires on a metal line is actually compliant once you account for the upper layer. The engineer sorts the violations into 3 piles. Pile 1. Real violations the design team must fix. These go back with a ranked priority list, sorted by ease of fix and timing impact. Pile 2. False positives the tool flagged that are clearly compliant. The engineer writes a 1-line explanation and dismisses them. Pile 3. Real violations the design cannot fix without a major restructure. but that the engineer believes are safe in this specific context. These need foundry sign-off. The engineer writes a waiver request, attaches the analysis, and starts the 48-hour clock. The foundry has its own engineer on the other end. They review the waiver, often ask for additional simulations, sometimes accept, sometimes reject. Acceptance means the silicon ships. Rejection means the design team eats a week of rerouting, possibly a metal mass change costing $10 million. That phone call from 2 in the morning Taiwan time. That is the waiver discussion. Wall 3. Allocation. Wafer capacity at the leading edge is a global zero-sum game. The foundry has a fixed number of wafer starts per month at 3 nanometer, maybe 40,000 wafers. The largest fabless customers book most of it 18 to 36 months in advance. Everything else fights for what is left. The Foundry Interface Engineer sits in the middle of that fight. Their company has a contract for a certain number of wafers per quarter. The foundry sometimes delivers fewer because a major customer pulled in a launch or a process tool went down. The engineer renegotiates, trades schedule slots, shifts product mix, promises future volume in exchange for capacity now. There are roughly 3 nodes the engineer manages in parallel. The newest cutting-edge node where the program lives, the previous generation for the cost-reduced version, a legacy node for the long-tail products. Each has its own capacity dynamics and its own contracts. A typical week. Monday, push the foundry to commit wafers for the next quarter. Tuesday, negotiate a swap because a competitor's launch slipped and capacity opened up. Wednesday, a phone call about a wafer that came back with a yield excursion. Thursday, planning the next process qualification. Friday, the weekly call with foundry program management. No software has the relationships. The engineer carries them all. Wall 4. Process change. A 3 nanometer process is not static. The foundry tunes it continuously. A deposition recipe changes by 2% to improve yield on someone else's product. A new etch chemistry rolls out to extend tool life. A litho rework reduces defectivity at the cost of slightly different transistor characteristics. The foundry sends process change notifications, sometimes weekly. The engineer reads each one and asks the question, does this affect our chip? For most changes, the answer is no. The variation is within the qualified envelope. The engineer logs the notification and moves on. For some changes, the answer is maybe. The engineer pulls test wafers from the new recipe, runs targeted characterization, compares to the qualified baseline, spends 2 weeks deciding, files a sign-off that the program continues unchanged. For a small number, the answer is yes. The product's critical timing path uses exactly the device family the change affects. The engineer requests an exception. Either the foundry runs this customer's wafers on the old recipe, or the design team takes a hit and the engineer manages the impact analysis. The foundry has dozens of customers. They cannot stop tuning for one program. The engineer is the firewall that catches the changes that matter and lets the rest through silently. Without that firewall, every weekly process tweak becomes a customer crisis. 3 reasons the AI hype cycle has not named this role, and the 2-layer winner that profits every time the phone gets answered. Reason 1. The work is relational, not technical. The output is a yes from the foundry, a scheduled allocation, a signed waiver. There is no artifact with the engineer's name on it. The credit goes to the design team for shipping the chip. The contribution is invisible by design. Reason 2. The decisions require context that lives in no document. Which foundry engineer is responsive at 3 in the morning? Which manager approves waivers liberally? Which capacity allocator owes a favor from last quarter? The information lives in the engineer's head and gets refreshed by every meeting, every email, every call. Reason 3. AI cannot predict whether the foundry will accept a waiver because it depends on the foundry's current yield position, the foundry's current capacity utilization, and the foundry engineer's personal track record. None of that signal is in any training corpus. Now the verdict. There are 2 layers. Layer 1 is foundry capacity itself. The winner is TSMC. At 3 nanometer and below, there is no real second source. Samsung's leading edge is a generation behind. Intel's foundry business is still ramping. For an AI accelerator that needs the most advanced node in volume, the contract is with TSMC. Non-recurring engineering of 50 to 100 million per program, plus per wafer revenue for the product's entire life. Layer 2 is the lithography equipment inside every fab. The winner is ASML. EUV is the only way to print sub-5 nanometer features. Each EUV machine costs $200 million, takes 6 months to build, and ASML has the only commercial production line in the world. Even if the engineer pivoted to Samsung or Intel, the lithography equipment underneath is still ASML. Both layers profit per advanced chip designed and per advanced chip shipped. Vertical capture that nobody outside the chip industry has reason to know about. Every quarter for the entire life of every advanced product, both checks get written. That is the Foundry Interface Engineer's job. One phone call, $200 million per missed window, 48 hours to convince the person on the other end that the design is safe. Next episode, the RTL Designer. Architect decides what the chip is. Foundry decides whether it can be built. The RTL Designer is the one who types it into Verilog one line at a time. Subscribe so you do not miss it.